In this video, we want to use Gauss's law and we want to find the electric field in two different regions. We want to find the electric field when little r is less than big R, the radius of the sphere, so electric field inside of each sphere, and then the electric field outside of each sphere when little r is greater than big R. Okay, we have two different spheres that we are going to do this for, an insulator and a conductor. Both have total charge of Q. Okay, so let's go ahead and let's start with the conductor and let's find the electric field. Let's find the electric field outside first. Okay, so the technique when applying Gauss's law is we want to pick a Gaussian surface that matches the symmetry of the charge that we're dealing with. So let me copy this over. And since we're dealing with a sphere, then our Gaussian surface should also be a sphere. Okay, so I always like to draw my Gaussian surface just so I know what I'm looking at. All right, and so if we're trying to find the electric field outside, we're going to draw a Gaussian surface that is outside of our charged sphere with a radius of little r. I guess I'm doing part B first. So Gaussian surface has radius little r, and it is a sphere. Okay, and so what does Gauss's law say? Gauss's law says that the electric flux going through our surface is equal to the closed integral E dot dA, which is equal to Q enclosed over epsilon naught. Okay, let's deal with the right side of the equation. So we have Q enclosed over epsilon naught, and since our Gaussian surface encloses all of the charge that we're dealing with, then Q enclosed is equal to just big Q. Okay, so the right side of the equation then is just Q over epsilon naught. The right side of the equation, it will equal one of two things on any AP physics problem primarily. It will either equal E times the area of the Gaussian surface, or it will just equal 0. All right, so why is that the case in this problem? So the electric field from this charged sphere is pointing radially outward in all directions. Okay, and the electric field at each point on this surface is the same, and it is perpendicular to the surface. It's going straight through the surface. So if I dot the electric field with the area vector, E times A times cosine theta is always just equal to E times A. Okay, and so the left side of the equation, closed integral E dot dA, will just become E times the area of the Gaussian sphere, and that's always the case. You're always looking for the area of the surface that you pick, not the charged surface. Okay, so if I set these two sides equal to each other, then we have the electric field times the area of our Gaussian surface is equal to Q enclosed over epsilon naught, or just Q over epsilon naught. Okay. Area of a sphere, that's going to be 4 pi little r squared, because it's the surface area of the Gaussian sphere. That equals Q over epsilon naught. And so E is equal to Q over 4 pi r squared epsilon naught. And if we were to let K equal 1 over 4 pi epsilon naught, then this would look like this. E equals K Q over r squared, which is just the electric field of a charged particle. Okay, so when you're outside of the charged sphere, it basically just looks like a charged particle. The electric field does. Okay, so now we want to figure out the electric field inside. I did this backwards. This is actually part B. So electric field inside of the charged sphere, we would pick another Gaussian surface and we would make it inside of the charged sphere, and it's going to have a radius of little r again, but now r is less than big R. and we would apply the same rule here. Okay, so let's go ahead and do that. So I'm going to have closed integral, I guess this is part A for the conductor, closed integral E dot dA is equal to Q enclosed over epsilon naught. Okay, and let's deal with the right side of the equation. So how much charge is enclosed in that volume is what we want to find. So how much charge is located in just this part. Okay, well, let's think about this for a minute. So this is a conductor, okay, which means that charge is allowed to move freely. Okay, so if you think about charge that is inside of this conductor, they want to get as far away from each other as possible. And so what is always going to happen for a conductor is the charge is just going to end up on the surface. All of the charge ends up on the surface for a conductor. Okay, and that's always. Okay, so I'll just kind of make a point here. So let's say that for a conductor, charge is always on the surface. Okay, so if that's the case, how much charge is inside of the sphere? There is none. Q enclosed is 0. So what does that mean? Q enclosed is 0, which means that the right side of the equation is 0. If the right side of the equation is 0, that must mean that the electric field is 0. So not only is the charge equal to 0 on the inside of a conductor, but so is the electric field. So electric field is equal to 0 inside conductors. Always. Another really important point. Okay, so now let's go ahead and deal with the insulator, because it's a little bit different. So for an insulator, and I wasn't very specific with this, but let's just say that the charge is uniformly distributed throughout the volume. Okay, which means it has uniform charge density. Okay, and so I will express our answer in terms of rho and in terms of charge, so you could see how to do that. And it just kind of depends on what AP gives you. Okay, so let's go ahead and let's just copy this sphere down, and we're going to do the same stuff that we did for the conductor, but for this insulated sphere. Okay, so we have, I guess this is, we'll do, let's see, part A is when R is less than R. We'll do that again. Okay, so if we want the electric field inside of this volume, we're going to pick a Gaussian surface that is inside of this volume with a radius of little r. Okay, so next thing we would do is apply Gauss's law. So that says that the closed integral E dot dA equals Q enclosed over epsilon naught. Okay, so how much charge is enclosed? This is the amount of charge enclosed. That's all we want. So we don't want all of the capital Q charge. We just want some of it. Okay, and so how do I get just some of that? We are going to use the idea that it has uniform volume charge density. Okay, and so since rho is charge per volume, that means that it is equal to Q enclosed over the volume of our Gaussian sphere. And it's also equal to the total, since it's uniform, it's also equal to the total charge Q divided by the total volume of the charged sphere. So we could put this in terms of rho or in terms of just capital Q. by setting up this ratio. Okay, and so we'll go ahead and make it in terms of just capital Q. So solving for Q enclosed, we have Q times the volume of the Gaussian sphere divided by the volume, the total volume of the charged sphere, and that is equal to Q. Volume of the sphere is 4/3 pi. In this case, it's little r cubed, divide by 4/3 pi big R cubed on the bottom. The 4/3 pi's cancel out, and so you're just left with Q enclosed is equal to Q little r cubed over big R cubed. Okay, so the right side of the equation then is, so Q enclosed over epsilon naught is just equal to Q r cubed over big R cubed divided by epsilon naught. Okay, so now let's deal with the left side of the equation, closed integral E dot dA. Again, this will always become either 0, typically either 0 or just E times the area of the Gaussian sphere or whatever surface you're dealing with. And so in this case, we're going to have E times 4 pi little r squared. Okay, and so we'll set the those two equations equal to each other, and we will solve for, that was a bad arrow, set these two equal to each other and solve for electric field. So we have E times 4 pi r squared equals all of that other stuff. So we have Q little r cubed over big R cubed over epsilon naught. Okay. Solving for electric field would be, so 2 of those r squareds cancels out 2 of those, so we're just left with 1 of them. So we would have E equals Q little r divided by 4 pi big R cubed epsilon naught. Okay, so that is the electric field inside a uniformly distributed insulator, charged insulator. Okay, so now we want to figure out the electric field outside of the sphere. So if I draw another Gaussian surface, let's say outside of this charged sphere, how much charge does this contain? It contains this whole thing, right? The whole thing. And this thing has a radius of little r now. Okay. So then applying Gauss's law, I have closed integral E dot dA equals Q enclosed over epsilon naught. Okay, the right side, how much charge does it have? It has all of it, Q over epsilon naught. The left side will again be E times 4 pi little r squared, and we set those equal Q over epsilon naught. So E is equal to Q over 4 pi r squared epsilon naught, which is exactly what we got for the conductor when we are outside of the sphere, right there. So same thing.